I'll just say hello real quick. For those of you that are joining in online, welcome. For those of you that are in the room, thanks for being here. Thanks for putting up with my nonsense. And we didn't get the Meetup page updated because I didn't get the title until yesterday, and then I was at work today, and so
it's just in time compiling. It's really
Don't bite
good.
the hand that feeds you.
But what's our title, Michael?
Why Rust is worth it. Fearless concurrency, no matter the paradigm.
All right, cool. Well, if at any point you find this to be useful or interesting or entertaining, or you just like his shirt, give it a like, and let's get rolling.
Cool. Yeah, I'll just introduce myself. I am Michael Edlinger, aka MK Edlinger, a username that I made when I was 10. You can basically find me anywhere that I have an account under that name. I am a tech enthusiast and software engineer. I did a couple of internships for AWS when I was in college, and then I worked for this little startup called CallForce here in Utah, and now I am at Ancestry. I've been using Rust for about 2 years now. It's kind of become my de facto personal project language of choice. And I've tried other languages like Zig or VLang or Nim or Kotlin, but I continually come back to Rust. And I find that it is a fantastic language.
You use it at Ancestry.com?
Yeah, approximately 0% there. It's a little bit of a bummer. Oh, and that actually reminds me, I'm going to try not to just like absolutely blast through and like talk really fast. So if you have a question and I'm not looking at you, please interrupt me. I'm trying not to go like crazy fast. So yeah, please.
Why did you drop your first I?
Yeah, it's my initials and then my last name is the username. That was my thought
So the
process.
E's in there twice, actually.
So it's MKE, so my middle name K, and then Edlinger.
He was,
K is not part of the
He was
mic.
10.
Yeah, I was 10, I was 8, I was 5, 2.5.
There's two. There's an Edlinger and E.
Yeah, the initial and then the last name.
I'm going to tell you right now, you did better than me. His name, my
Hey, it could have been something offensive, you know what?
And he didn't know how to do it, and it just stuck.
And it just stuck.
Fair enough.
Cool. So first, I feel the need to kind of argue the point of my of the title, and you might ask, you know, worth it? Like, why would you imply that Rust is not just the best all the time, every time? This is a Rust meetup. What are you trying to say? And yeah, I would say that I'm not even just implying that Rust isn't always the best. It's just not. But I don't know if anybody's trying to argue that. But the purpose of this talk is to kind of look at when it is, because Rust is an incredible language. And there are some strengths and weaknesses that we can look at. Like, for example, I am doing the Advent of Code this year, which for anybody who doesn't know, that's like 25 problems, one each day from the 1st of December to the 25th. And they're just little problems. And in this scenario, I've been using Rust. And it's actually kind of been painful because, you know, these aren't problems that need like long-term maintenance. They're not, performance isn't really important. And the complexity of Rust is almost wasted on these problems. I don't know if that's taboo to say, but
These are problems like, you know, reverse the letters and do little simple
exactly.
things.
You look at this palindrome and
Things to
whatnot.
use that work all the time.
Yeah, exactly. So it's not that important, but when corrected, so you can see my little tagline here. When correctness and performance aren't always paramount, but when they are, Rust is killer. And so that's what we're going to explore today. Why is Rust so good in these scenarios? And to be clear, I still use Rust where it's maybe not the best anyways. I love Rust. It's great. Sweet. So here's what we're going to be doing today. We're going to be looking at a kind of toy problem. It's called the 3n+1 problem, also known as the Callout conjecture. Veritasium has a really cool video. Have you seen it? It's really kind of a fun toy problem. It's super simple. The only reason it's interesting is because it's deceptively simple. In the mathematics world, it's something simple enough you'd think there was a formal proof for it. However, there is not. As just a way of introduction to this, what this problem is, and the simplest way that I can say it is that for any positive integer n, the algorithm shown there will eventually reduce to 1. So if I chose 8, essentially the conjecture is that 8 will reduce to 1 if you, whenever the number is even, divide it by 2, and whenever the number is odd, multiply by 3 and add 1, and then take whatever that is and keep going until you hit 1. And the conjecture is that all numbers, all positive ints, will eventually reduce to 1.
But the number of iterations is unpredictable.
Exactly. The entire nature of the problem is quite unpredictable, which is why it is still a conjecture. Even though it's been, I think, brute force up to 2 to the 68th. So it still holds true for everything we've tried. The problem doesn't really even matter. It's kind of a toy problem to show these different things that we're going to try. We're going to explore doing the coalesce conjecture for a set of ints with a couple different paradigms. First, we're going to try single threaded, just a really simple implementation. Then we're going to start moving to multiple threads. And then we're going to look at what it would take to go to multiple computers, aka network service, aka asynchronous Rust. And we're going to look at what the characteristics might look like for each of those. Any questions so far? I'm trying not to blast. Cool.
So far, so good.
Sweet. So we can look at our single-threaded implementation first. I chose to do it in JavaScript. JavaScript is pretty simple, and there's a pretty good chance, at least most of you have written JavaScript before. This implementation is super simple. We can just see that I'm looping over from every number from 1 to 1,000,000, and for each of those numbers, we put it into the while loop, and we don't actually even test anything. The idea is that if this program completes at all of the numbers were indeed valid, a valid part of the coalesce conjecture. And we're going to try to quantify some of this. So I'm going to plug this into Hyperfine, which is it's a benchmarking tool that's pretty nice, and it gives us some pretty good surety that we are not getting outlier results for what we're doing. So if we run this algorithm in Hyperfine, we can see how fast it completes.
What is this container?
This is me SSH'd into my server at home.
No.
What's the
outside part?
like
What is your
like this?
presentation in?
Is this just Tmux plus?
You're asking what's that?
Yeah, so this is Biobu. This does the multiplexing for my terminal, is Biobu. And this is how I can switch between terminal windows that are on my server. And then the actual presentation software is called Look at Me. And it's just kind of this terminal presentation
Okay, so you're
software.
running Look at Me inside of Tmux.
Inside of Tmux, over an SSH connection. So
Layers.
it's
With a
yeah.
carrier pigeon in between.
yeah. Anyways, we cool. It ran, and it ran pretty fast. It averaged about 1.4 seconds. So in this single-threaded node implementation,
To check the first million?
to check the first 1,000,000,
Wait,
Yep.
you said it averaged, so I mean it ran it a bunch of times?
it ran it 10 times.
Oh, okay.
And that's what Hyperfine does, because otherwise we wouldn't be that sure whether or not the one run I do is that representative.
Gotcha.
And I'm about to show Go code being worse than Rust, and that's when everybody starts to come out and
That's normal.
that is normal. I mean, I guess this isn't a Go meetup, but
Well, here's the question. Are you using the naive implementation in Rust or the finely tuned implementation?
I am naive in both Go and Rust, so we'll just make
Okay,
that
that's fair.
assumption.
That's super
Yeah, yeah, yeah. You'll see that with the code examples.
Well, because sometimes that makes a big difference on the, if you take what the average person would do versus what the person who knows all the ins and outs.
Yeah, I'm sure if there are any Gophers watching this, then I'm sure they'll see something that could make it faster. But
Challenge accepted.
Okay,
Yeah.
I'm looking.
yeah, if they can make if somebody who knows
Oh,
Go.
wait, we're just doing a for loop. Okay.
Yeah, we're not getting that complicated yet.
Picked, where it's very simple to code.
Yeah, very simple to code and very simple to look at on a slide. So anyways, with this implementation in Rust, as you can see, I mean, it's very simple. It's very similar to what we were doing in
Gotcha.
Node anyways. So let's look at how well this performs. We'll go and build it. Seems I've built it before. And nope. Okay, there we go. Sweet. Awesome. So we did it in about 115 milliseconds. This is about an order of magnitude faster. And this might be something you guys expected. It actually wasn't. I wasn't expecting it to be that much faster. So I actually put the code into Godbolt to see what the actual assembly was, just because I thought maybe the loop got optimized away somehow or something. And no, it's just that much faster, which is awesome. But it actually kind of hurts a point that you'll see that I've tried to make a couple times, which is that often garbage collected languages are kind of good enough. The Debian Linux distro, they have a team that they have dedicated to this benchmark game, and that's what they call it. And they just implement a couple problems in multiple different languages. It's by no way authoritative, but it's kind of an interesting way to kick the tires. Go ahead, yeah.
Oh, nothing. Nothing. I was just stretching.
Oh, sorry. So what we can see here is that for the most part, this is kind of what we'd expect. Rust is 100% of the time faster. But what we might not expect it is, while sometimes Rust is many times faster, like for binary trees, we'll see that like Rust versus JavaScript, it's roughly 7 times faster. But we can also see some cases where it's not that much faster. Like in the pi digits benchmark, Rust goes in about 0.7 seconds, where Java is in about 0.9, which is only about 0.2 seconds off, or kind of comparable. It's not too crazy. It's not too far off. And so why do I bring this up? The point is to look at Rust and say, well, where does it bring benefit? It has some increased complexity that comes from being a kind of harder language to learn. Where does it like really take off?
Come see what's left of my wares.
And and the answer is during concurrency. When you're trying to do things fast and correct at the same time, Rust really kicks butt. So now let's look at a semi-naive implementation of something that's actually parallel. Let's try to use some threads. You'll notice I've switched from JavaScript to Go, and the reason is because it's just basically impossible to do anything parallel in JavaScript. You can ask Jesse, Jonko102, who actually did attempt to write parallel multi-process node for this particular problem, and that was rough, apparently. So we're switching to Go.
You build it out as a web service.
Yeah,
That's
yeah.
how you do it.
I suppose if you only wanted to be a couple times slower. So here's the Go implementation. It's pretty simple. Essentially, we are going to go and create a Go routine for each one of the CPUs that we have on this machine. And for each of those, we're going to loop over, grab a number from next, which is just a unsigned 64-bit int. We're going to go ahead and check and make sure that we haven't gone over the number that we're hoping to compute to. We print the number, we compute the coalesce conjecture for it, and then we increment next.
Are 64-bit int operations atomic?
So that we might wonder is this code correct? Will
I mean, it wasn't a great segue.
No, that is fantastic because
Where's the $5 show up?
yeah. Well, we might wonder.
Before.
Yeah, experienced programmers. I'm glad that you could actually see that directly immediately. This program that you would probably expect, given the question you just asked, would you say that this code is correct?
No, I don't think so.
No, I don't think so either. But the question is, will it compile? And if it compiles, what will the output be? And
I think Go will probably let it compile if you don't run any of its linter stuff, but I'm not really
let's take a look.
expert.
You're looking pretty expert.
Oh, yeah. Well,
Yeah. So it does
Go
compile.
FMP.
I literally spent all of yesterday and all of today reading the Go book. So.
Yeah. Oh, okay. We have a betrayer.
Didn't you start this whole presentation with the Rust is not the only language?
Yes. Yeah. No. Go, the compiler, at least, will not complain about this at all. compiles very quickly. Good job, Go, with no complaints.
Yeah, in the book, all the time they're saying, yeah, it's on the programmer. It's on you to like use this stuff correctly.
Yes, as with many languages, except for all of them, including really good C++ programmers like the ones who write browsers and operating systems, who never write memory safety bugs. Yeah. Well, anyways, the point of this, which you so astutely saw, is that this is not going to run deterministically. It's going to vary wildly. This has a race condition. We've done something wrong. I can't imagine a circumstance where this is the expected behavior that you were looking for.
Unless you wanted to make fun of Go as some other languages.
Absolutely, which I would recommend. In Rust, however, let's try to do much of the exact same thing. I literally, line for line, I'm trying to copy what we just did in Go. We're going to loop over, create a thread for every CPU that we have on the machine, create a vector of all of our threads, and for each of these threads, we're going to loop over, grab a number from next, make sure it's not greater than up2, print it, compute the coalesce conjecture, iterate next. So much the same thing. And we might wonder, is this program correct? Obviously no, but are we going to have the same issue? Or is this going to behave the same way? And no, it's not. And the reason it won't behave the same way is because it won't even compile. Rust is smart enough to look and say, you are trying to borrow next in this loop, and you're borrowing it multiple times, one for each thread. That is going to create a race condition. We're going to have a problem. Rust won't let us get to the runtime to see how poor it is. And something you might have noticed too is in Go and in Rust, I iterate next after I compute the coalesce conjecture. And I do that because if I put next, the iteration of next, right after I pull num equal to next, the Go code actually behaves. I wasn't able to reproduce the race condition a single time. So you could be tricked into thinking you have correct code. You could have something in production, and you might look at this code and you could say, well, this is, I mean, obviously we saw it very quickly, like anybody could see this. But tell me that when you're looking at 100, 200, a million lines of Go code, and you get a race condition. You could end up having something that sneaks in there, and in a million lines of code could be very difficult to find. So what does Rust provide for us to save us from this? There are essentially three different things that I think really set Rust apart. First, there's ownership. Ownership is essentially three rules, which I have shamelessly copied from the Rust book, the excellent Rust book. First, each value in Rust has a variable, and that variable is called its owner. There can only ever be one owner at a time for a given value, and when the owner goes out of scope, the value will be dropped. There's also rules for references. There can be one mutable reference, XOR any number of read-only references, so either one or the other. And we can kind of see here in this little code example that I wrote up that we have this value, a vector of usizes, right? So that's the value, and the owner variable is the owner of that value. On the next line after that, we have a mutable reference that we are taking, and that's also fine, but when we get to the third line and try to get a read-only reference, then we are going to see a problem. That would violate the rule of exactly one mutable or multiple read-only references. The reason that this is important is it helps answer some questions that the Rust compiler needs to know to prove that our program is correct, which is who can mutate a given value, and who's responsible for cleaning it up, right? In our Go implementation, who can mutate a value is a very important thing to know if you're going to be trying to mutate it from multiple threads at the same time. There are some guarantees you want around mutation from multiple threads. And then who is responsible for cleaning things up? This problem is related to double free memory issues or use after free memory issues, where you don't want those. Those are memory safety issues that Rust tries to protect us from. Anything so far? I'm realize I'm looking at the screen a lot, so cool. So the second thing that Rust has are traits. Traits are not too unlike interfaces that you would see in Java or other programming languages. I'm not super familiar with Go's idea of interfaces. But anyways, traits are not too unlike that. But we're not really focusing actually on that idea of traits. I'm thinking more of something in Rust called marker traits. And these marker traits are managed entirely by the compiler. For example, you can't implement any of these traits for types that you create. They're implicitly defined. And they represent some properties of types. And they help the compiler ascertain whether or not your program is correct. Specifically, when it comes to concurrent code, there are two traits that are very important to us. The sync and send traits, both of them being marker traits. The send trait essentially answers whether or not the type can be safely sent across threads. And an example of a type that is send is an atomically referenced counter. These values actually are, I guess maybe it's better explained from the counter example. Something that is not send is just a normal reference counted value. And the reason that this would not be send safe is that it can't atomically synchronize the reference counts. You could think of a situation where two different threads are trying to decrement the reference counter, and since they don't do it atomically, you could reach a race condition where something is trying to be double freed. Then we also have the sync trait, which essentially is kind of more abstract, but essentially describes types for which it is safe to share references between threads. And this type manages whether or not something can be safely mutated from multiple threads. An example would be a mutex, which we're about to look at, and actually make a multi-threaded example that's useful. Something that's not valid is the Rust's cell type, and that is something that provides interior mutability, not too unlike the mutex, but it has no synchronization. It has no ability to, yeah.
So you said that these are automatically generated? These
Yeah.
traits? And you can't define them yourselves, and the compiler just decides for itself if it can use it or not?
Yeah, basically. So there are some types that are in the standard library that Rust provides that it just knows implements these traits. And there are some general rules that Rust can say that it can look at and say, well, if your type is in a type that is sync, then I'm just going to call the whole thing sync, and it can all be moved between. I'm going to be honest, I'm not sure entirely all the rules for how it
That's
does
pretty much
that.
it.
Yeah, oh, okay.
If it's all send, if your thing that if your struct that you made is made up of all send and all sync, then it will be send and sync.
Yeah,
And if there's anything in it that's not, then it won't be.
yeah.
Is there an example of that's not? I'm not so familiar.
There's lots of stuff that's not send and sync. Well, I mean,
Most things, really.
lots.
Most things?
Yeah.
No, all the primitives are send and sync, and a lot of your standard library types are send and sync. But like a file descriptor might not be, and the arc in the cell, or I should say the reference counter, the RC in the cells aren't. And there's a few things.
Yeah. I also found that for a little while the send and sync distinction between the two was a little bit hard for me, but it seems to mostly make sense.
It syncs I think I want to use an immutable reference shared across threads. If it's not sync, you can't.
Yeah, because I guess you wouldn't need any kind of synchronization for mutations just to know who needs to clean it up.
Yeah,
So.
something.
Cool. This one. RAI. This is actually probably my favorite. I think this sets Rust apart a lot, at least from a lot of the programming languages I've used. RAI stands for Resource Acquisition is Initialization. And a good way to explain this is actually by looking back at our Go code. So what was wrong with our Go code? We didn't have a lock. We didn't have a mutex. We had no synchronization between our threads or our Go routines. And a way that we could have fixed that is by defining a mutex lock, locking before we access and mutate next, and then unlocking it when we're done with next.
So,
Yeah, go ahead.
just for reference, the proper way to do this in Go would probably be to use a channel.
I've heard they like channels a lot. Yeah.
Yeah,
They have line channels.
I've heard things like channels a lot.
I think that's true in Rust as well for this
Those.
problem, so.
Yeah,
Okay.
Rust also does.
I think that's architecturally a better approach.
I would just use Rayon.
Channels orchestrate, mutex is serialized.
Just do a range of 0 to 1 to 1 million and just roll.
Man, it would be terrible if that was an example later.
Go concurrency like this is like channels is just a abstraction layer across the Mutex
Yeah,
system,
I'm actually
whatever
familiar with
it
it,
is. So that's why you would lean towards it in Go. I know there's only like 2 things that you can do in Go to like actually
Yeah.
do this, but one of them is a wait group.
Yeah.
So he's absolutely correct. We'd do it with a channel, and it would be fine, but it would work pretty much the same.
Yeah,
So-
and for the most part, you might think that this is kind of contrived that I chose this example, and it is actually. I chose it on purpose to be able to do the RAII comparison. So
If it can be done, a junior programmer will find a way to do it.
yeah, I believe it. I believe it.
Yeah, we will.
Yeah, and so besides these things, you might look at this code and say, what's wrong with it? Because it's technically correct. I mean, it will do what we want, right? The output would be what we expect. And really, there's nothing fundamentally wrong with it. But the issue that you could find with this is that we can misuse it. We can cause a race condition. You can acquire the resource next without properly initializing the environment for it, without properly locking the lock. So in this case, resource acquisition is not initialization. It doesn't. We can acquire it without properly initializing things. And yeah, this code could compile, as we saw, just as well without the mutex. Rust won't, or Go won't save us. Things are a little different in Rust. For this type of definition, I'm going to try to go with the latent pointer. We'll see if it's worth it. In Rust, the mutex that we create here, we can kind of mostly ignore the arc for now, but the mutex that we create actually encloses our value, our unsigned 64-bit int. And if we want to access whatever this int is and mutate or do anything with it, we're going to have to take this mutex and call the .lock method. Otherwise, we have no way of interacting with the U64. We have to call the .lock, and it will return something that's called a mutex guard. Upon acquiring this mutex guard, the mutex will be locked, and the only way that we can interact with this U64 is through the next guard. As long as the next guard is in scope, as long as we have the ability to access the next variable, this U64, this mutex will be locked. The only way to unlock this mutex will be to drop the next guard, and therefore have no access to the U64, no ability to mutate it. You could almost say that by acquiring or locking, we have properly initialized everything that's expected. And it's not to say that this is impossible to misuse. Deadlocks are still possible, but memory corruption certainly is impossible. And race conditions and memory safety issues are not going to happen with this paradigm.
And we don't even have to worry about unlocking.
And we don't even have to think about it. Unless we want to, as we see here. Unless we want to. This is just me editing our previous examples to add the lock and to make it so we can actually see how this performs. This code is much the same except for adding the lock, and let's see how this works. So we're building it, and then we're going to run it in Hyperfine to see how it performs. The answer is very fast. So this implementation is able to run in about 132 milliseconds. It is not slow. But if we compare it to how Rust behaves, we might want to look at this code. This is basically, for the most part, the same, but we can actually see this code is exactly what we saw in the previous example. And something that you'll notice is that I have chosen to put it in its own scope. You'll notice I say that the lock will only ever unlock when next guard is dropped. And I could wait until the scope naturally ends here. But that means that I'm going to have to wait for the whole colette's computation. And I'm no longer using the next guard. So I can actually put it in its own scope. This will ensure that it's dropped here and before we do the
And it's
computation.
acting the same as the Go code, where it unlocks right after.
Mhm.
Exactly, much the same. You could also just call drop
Mhm.
on this. I guess it's a stylistic choice. So sweet, this is much the same. Let's take a look at how it performs.
Faster.
Yes, indeed. a good bit faster.
Halved it.
Yeah, a little bit more than half, but yeah, this is quite a bit faster. Not having a garbage collector is very fast. But this isn't the only thing that it affords us, like what Daryl was talking about. We can use confidently third-party libraries like Rayon. All of the code that I wrote here, basically all of it, with the Rayon library could basically be condensed down to these 3 lines. And we can be confident that it will be safe and fast and excellent. Stay excellent.
If you get the rayon, I'm sure with crustacean on
Cool. That concludes the parts that I am actually okay at.
Did you run the rayon? Did you run the rayon code to benchmark it?
I had a shirt made out of rayon once. It was
No, actually I didn't. I wonder, yeah, I don't know how that would perform.
Touch a
Yeah.
file.
What's going
You
on?
guys want to see it? Okay, let's go and,
We want him to run
You have access to it from that terminal.
the rayon code to see
I do.
if it's any faster.
let me,
Oh, yeah, we totally gotta run the rayon code.
yeah, let me see if I can find it really quick.
And then we should do channel implementations. Does Go, I assume Go has a non-locking channel implementation, right? I mean, they're so based on channels, they've got to.
Non-locking?
Non-locking.
That's the default.
Non-locking.
Oh, non-locking?
Yeah, it doesn't use interior locks. I mean, the
Let's
cross-stream
see.
channels don't.
I'm going to, how can I get to this really easy? Okay, sweet.
What channels don't?
Cross-stream library, that's the kind of channels you should use in Rust. Not the standard libraries ones.
Right.
They're made by the same people.
Okay, sweet. Yeah, I actually do have the ability to check.
All this stuff.
let's see.
And other stuff. That's one of the most downloaded libraries.
Cross-stream's good stuff.
Oh, I don't know if this is, yeah. Okay, so there's 2 potential things. You'll notice this is actually quite a bit slower. I suspect that there's 2 different things. I actually only have that code written as a test. So maybe there's some
You
unfortunate.
didn't do it in release mode.
Can you just
Yeah.
test it in release mode?
You
I
can
didn't know.
change your tests so they run in release mode. There's a
Oh, it probably built for the first one. Okay. Okay, that's far more comparable, actually. Wow. Well, compared to what we were experiencing here, right? So we had 74 milliseconds. This one's 84.
Eight. Yeah.
That's comparable. It's still faster than our Go code, so that's cool. I also wonder, something that you might notice about what Rayon has to do is it actually fills out, it takes that range and it fills it out into an array, I think, to cut up between its work stealing workers. So I think that there's a cost associated with that.
There is a bit of overhead to how rayon works.
Yeah.
So
So,
you get convenience. You
but the
get
convenience is excellent, and we're going to use it.
Oh, that
and-
overhead of 10 milliseconds. Oh.
the overhead, unbearable.
Depends on what you're doing. If it's a game, that's a big deal.
Yeah.
I didn't have to.
Cool. Yeah, now we're going to go into async land. This is kind of a speed run. This is a rough introduction. We've done everything that we can do on a single computer. Now we're going to the network. And to be fair, a lot of code these days is network services. A lot of code is being run in this space. And asynchronous is kind of a fantastic buzzword, and rightfully so. If we want to have a network service, we likely want to be able to handle many user requests concurrently. And we could do that with threads, but it'd be highly inefficient. And there are implementations that do use threads, but yeah, async can do it a lot better because threads can be expensive. They can take time to create. The operating system kernel is going to need to manage them, and every single one is going to need its own stack space. So it's not only computationally more expensive, it's also more memory expensive. Each thread still, if we do choose to do this, is effectively only going to be able to handle one request at a time, since I/O is blocking. Asynchronous code can effectively alleviate these issues. Instead of spawning different threads, we can instead abstract over something that is more task-like. In Rust, they're called futures. And while a particular task is waiting on I/O, we can have the runtime go and work on something else. As like a simple introduction, we can look at something that is roughly comparable, which is a synchronous and an asynchronous example that do basically the same thing. So in this first example, we have a synchronous function, get two sites. It's going to spawn two threads that are going to supposedly download a website and then join on them at the end. The alternative looks pretty similar in asynchronous Rust. We are creating two futures that represent the work to download these two websites, and then we are going to join on them. And this is actually an answer to a question I had, is it really that much faster? How much faster is it really?
So much.
A lot faster. Yeah, it actually kind of shocked me. I just made a little test that essentially does nothing but go over a loop of 10,000, and for each iteration of the loop, it creates a thread and joins it. That's all it does. And the async example literally just creates a future and awaits it. That's all they each do. Threads took 357.
Spawn 10,000 threads. What's the stack size for thread in Rust?
If your futures didn't do anything, they might have been optimized out. Rust has
Yeah.
lazy futures that literally don't do anything anyway until they need to do something.
Yeah.
The point. Did you cheat?
Very possible. Very possible. I would. I blamed the compile. I didn't compile in Tart.
Memory footprint for 10,000 threads with a stack for each one of those.
A lot.
Significant.
It's two megs per stack by default on most operating systems.
Well, if you also want to see, I actually have
So
the
that's 20
code.
gigs of RAM.
Something like that. Math in my head is not my strong point.
So it was swapping.
This is the actual code that I did. Essentially, it's only one thread at a time, one after the other, synchronously. All right. So spawning this thread that does nothing, joining immediately.
Okay.
And then-
and it's ending right then. Okay.
No, not in parallel.
So it's not all at the same time.
No, and you'll notice it's the exact same thing that I'm doing here in the asynchronous code. This is being awaited. This loop is doing one after another. So these are not concurrent in the way that I've written it.
I'm really curious to see what the assembly is for that code.
I
think
did.
it's
I
optimized.
thought it was all optimized.
'Cause there's
This
nothing
is
to
just a
do.
single thread.
Yeah.
This is an OAuth. Just go.
Yeah. Like
Well,
for Criterion to,
I wonder-
if you even just use literals, you have to wrap them in a black box construct to make sure the compiler doesn't fold things away.
Yeah. Well, I wonder, this wasn't abstracted away. This took almost a half second.
Well, that's because it's making a syscall. The compiler can't abstract away a call to the operating system to ask it to allocate a thread. So it's literally calling into the kernel, and then the kernel's going and doing its thing to give you the new thread that you asked for, and then you're like, haha, just kidding, let's shut that down, and then it's going to go shut it down again, right? So you're
Yeah.
leaving your Rust code at that point. So that can't be optimized away.
This
Yeah.
is part of the zero cost abstraction thing because it's saying,
Yeah.
okay, I see what you're trying to do, and okay, fine,
Yeah.
we know it's correct, but I can optimize all this stuff out, and I know it's safe.
Right.
So Levi's got a comment. He says Linux threads are cheap these days, but they definitely still have a little bit of overhead.
Yeah, I mean 300 milliseconds, something like that. 100 milliseconds. That's still freaking cheap.
300
but-
milliseconds for 10,000 threads. That's
Yeah, it's still super cheap, but
Yeah, the only time that you're going to start seeing this being crazy is if you want to take on a million concurrent requests.
Your point is still valid, but
Yeah.
if you did something like add 1+1 in the thread and add +1+1 in your async, I think that it fixed your async, so it actually took some time, but I still think it'd probably be an order of magnitude or two faster than that overhead of starting.
If we're curious enough, do we
it.
want to group
Do
program this?
Do it.
Is this what we want to do? Okay,
Let's
let's.
see it.
In fact, to ensure, do you think it represents any significant burden to use like an atomic int and just continually?
That's gonna do something in your hardware to sync things. What if you like just grabbed a duration and returned it? Like you don't even have to use it. Well, maybe you do have to use it. I'm trying to think what will make sure the compiler doesn't
Yeah.
throw
Well,
it
I'm thinking
all away.
the only reason I'm thinking to do an
By
async
pushing
int
it to your
is that I can keep going into it, take the async int, iterate it,
Oh, yeah.
go out, go back in, iterate it.
There you go. That would work.
That's what I was
You could do the
thinking.
same thing with a thread where you actually give the thread a value, you increment it, and
Oh.
then you return the value when you join, and you unwrap it, and then you give it to the next thread.
Okay, my
You
hint.
could do the same thing in both, where you're giving something a value, incrementing it, and returning it. That way,
Should
it
hinting
can't
that
be optimized
Yeah.
away
Yeah,
because
just
there's a
restart,
value.
reload your memory.
Yeah, let me
Yeah, and
restart
print
that
them
really
out in
quick.
the end, sure.
Um,
Although, I mean, if you're incrementing a number 10,000 times, you know what the number's going to be.
but does the compiler see that's?
But does the compiler?
It better dang well no.
It just does that logic. It's like, well, it's gonna end up being 10,000.
Optimize.
I've seen
It doesn't actually compute it.
It'll do that for loops with
No way.
constants. Yeah, sometimes it will.
I've seen code get completely optimized away for that very reason if I don't do something
Yeah.
like print it out. because
Does anybody
this
remember?
is not-
I'm trying to get like an
It's not
atomic
actually
U size or
using it,
something.
yeah.
What do I need here?
I was gonna say if you just did the
I've
1
never
plus 1,
used
it still
atomics.
probably
So
wouldn't do
I
it.
don't think you
It's
need
like,
to use atomics.
Is it? Oh, it's sync. Ah.
Well, I guess you might have to for your.
I mean, if you don't care about the
See?
results, you may not be atomic.
Well, I need it so that
Like,
Rust.
Process it, do a thing.
I need it so that Rust will let me.
Yeah. Just put it on
Let's
safe
see.
block, it'll be
I
fine.
need to make Rust
For the
bad.
threads.
Oh, every time I've tried to use it on.
Oh wait, my whole suggestion
Failed.
of passing a value in and back is going to measure our synchronous end-to-end time. That's not what we want at all. We want to do it all in parallel.
Well, but that's sort of the code that we have now, right? When it's
Well-
creating a thread and
I
joining
think
on
the
it.
demonstration
So-
is like, yeah, I like your spinning
So if you
threads
look at the
is-
overhead
Yeah.
of the thread
You might as
creation,
well
that would
just
be
send
a valid way of looking at it.
I don't know. I think I may have set us down a rat hole where your point was valid anyway.
Well, if we want to go and experiment with this, because it'd be interesting to see that we can, or we can keep going. Either way. Yeah.
Already
Not going
down this
anywhere.
path.
The hard part is like verifying, is it actually doing what I think it is? That's where you have
Yeah,
to
let's
open up
read.
your
Let's pull up the
settings
assembly and read through that.
That's
sometimes.
possible.
You'll have to separate them into separate binaries though, if you want to be clear.
This is where I.
Has anybody ever really used atomics? They're always such black magic to me.
I mean, I've used it in other languages, but that's
Yeah.
like in
I
the
used it
Java.
in
in Java
They were-
once, but
Syntax sugar over.
Does Java abstract away the difference between platforms? Because I know the
Yeah.
atomics are different than.
Yeah, so you
platforms.
can get like an atomic int, but that's got like methods to increment it.
Sweet.
Yeah, that's pretty good. Straight up the head.
I've actually
Modification
used.
exception today.
So Levi chimed in, it's atomic U size, capital U, capital A. If you wanted not U64, but just U size.
I think they're going to be equal because I have a 64-bit processor here. So hopefully
Yes.
Hopefully that works out. All right, let's go see if I can find that code. It's here somewhere, I promise. Okay.
Could you perchance bump up your text size?
In the terminal or on this?
Definitely on that. Absolutely 100% on that.
Yeah, well, I can probably.
there you go.
Boom, boom.
Hey,
Ta-da.
oh my, okay, ta-da. Yeah, there we go, sweet. Cool. Yeah, I think async's still a bit faster.
That's a little close, man.
Still a bit. I think, but
Wait, the async took longer.
No, microseconds.
It's microseconds.
No, compared to the last time you did it.
it did because it was taking
That's
20.
a good sign that it actually did something.
Hey, there we
It went from
go.
20 to 700, so I believe the 700 number.
Yeah. So I now I even feel stronger about the point. Yeah. Yeah. So sweet. Let's actually look at it as a async Callout service. Async so cool. It's way fast. Amazing. Wow. Not 20 microseconds fast though. That's honestly a deal breaker.
But we should point out though that the difference is the overhead, right? If you actually had to do a long computation, async's doing that on one processor. So the 300 milliseconds overhead of making all those threads wouldn't make a difference if each of those had to take 2 seconds to do something.
Yeah. No, that's valid. Yeah.
Right, tool for async is for
Well-
concurrently waiting for things. Right?
No, it's not just about concurrently waiting. It's about being able to handle concurrent throughput. Because of the stack size, there's a limit to the number of.
Well, that's a good point.
Yeah, because when people talk about async, what's super exciting is that you can start talking about, can we handle 1 million concurrent requests?
Right, but that only works because when you're talking about requests, most of your time is spent waiting.
Yeah. Well, and wouldn't it be terrible to spin up a whole different stack just to wait?
Yes.
That's how Apache used to do it, right?
Yeah, I think it's actually not so bad if you do like thread per core or something like that. There's some, I don't. Anyways, sorry, Daryl. What do you
People
say?
here remember the so-called 10,000 simultaneous connection problem that I think Nginx was the first one to solve. People using Tomcat couldn't have 10,000 simultaneous connections, but Nginx was able to do that because they had essentially rolled their own in C code version of async await stuff.
Yeah.
So they were not spinning off threads and were not allocating all that stuff, and they could maintain 10,000 connections at one time.
And that same stuff is boiled all the way down.
How long ago was
into
that? 10 years ago?
Oh, it's like 2006.
Age?
15
Not
years
good
ago.
enough.
That was just mind-boggling that you could do that.
It was before 2010 for sure.
And then how much after that did Node.js come out? Just within a couple years or something?
Somewhere.
Yeah.
I know I was using 0.12 in like 2013 for Node.
It was very shortly after that Node came out. And that was part of the motivation for us saying, hey, if we do this thing. But when I think of how async await works, it just reminds me of all the cooperative multitasking we had to do back in Windows 3.1 days or Mac OS 7 days and so forth. It's just everything old is new again.
Multitasking is much better though when you actually have multiple cores and it's all within your code that's cooperating. That combination makes it much nicer. Not like, gee, this program over here is hogging the processor, and so now my UI is unresponsive. That was no fun.
Yeah, no kidding.
Trust everyone to be a well-behaved programmer.
Cool. Here's just kind of a speed run. We already talked about futures. They're essentially anything that implements the future trait. They're a unit of work that is not too unlike JavaScript promises as a concept, at least. And the future trait is part of the standard library. This is, not set in stone, but relatively stable. And then we have the thing that actually executes these futures or tasks, and that's called an executor or a runtime. This is what polls the futures, kind of continually progressing them. And there is not an implementation in the standard library. There's no blessed implementation. This is kind of up to you to find one that fits your needs.
This is the standard.
Uh-huh. Yeah, so there's Tokyo. It's by far the most popular currently. And
So we
it's,
looked at the trend lines, how standard versus Tokyo doing.
Yeah. I've never been into concurrent much. Have anybody else? Curious to know.
Thread stack size is 2 megabyte by default, but you can set it to what you want. I imagine the kernel will want you to use at least one page, typically 4K.
well, I think in what is it? For GNU Linux, I think the default has been for your starting thread 8 megabytes.
Right.
Right. So when you spawn a new thread, that's runtime dependent. But when the system starts like a thread, or a program, I like before it gets to anything else. I think it's default to 8.
So forking at a smaller stack, potentially.
Yeah. Cool. Yeah, and then we have
Starting a thread is different, not under Rust control.
Huh?
The starting thread is different, it's not under Rust's control.
Yep. At least that's my understanding. We also have the async and await keywords. They essentially desugar down into some state machine of futures that the executor can use. There are some pretty cool articles that talk about what async await actually desugars to. That's above me. I don't know that. Cool. So we're going to kind of speed run actually making a callout service, because async honestly could have been its own talk, but kind of made sense as like the tail of this one. So maybe this is a nice intro to get us curious enough for whoever talks next, and maybe even talks about async Rust and tackles that. Some brave soul who's braver than I am. So to make this service, we're going to take in a couple dependencies. You can't get away doing async without them. We're going to use a simple gRPC service. So Tonic is going to be our gRPC server. It manages a lot of that. Prost is going to generate some of our Rust bindings for our protobuf definitions. We're going to use Rayon to actually do the callouts computations, just because we can. We're also going to use request to make a call to another API, just to make this example a little bit more believable. We're going to use Tokyo as our runtime, and we have a build dependency on tonic build. Rust has a cool thing where we can essentially have some build steps that Rust will run for us. For example, it's going to build our gRPC service definitions into Rust code for us and kind of seamlessly integrate it into our code base. Here is our protobuf definition, or our gRPC definition for like a really, really simple service. Our callouts service. We have one RPC call that we can do, which is compute. It takes a range of values to compute over and returns a reply, which is how many milliseconds the computation took and some message that we don't know yet. This is our build.rs. Essentially, what this is doing is compiling our service.proto to actual Rust code that we're going to use later. And this is how we're going to use it in our code. Tonic comes with a macro that's very helpful. These two cooperate together. This will put our Rust files somewhere. This will detect where it put it and bring in this module. We also have the types. So this is where we are bringing that into our code base, and then we're using the types that just got generated here, like our range and our reply. And all of that boilerplate so that we can do this. Actually define and implement our compute function that is taking our request, which has a range. It does all of the validation for us with Tonic, and then returning some kind of response that has our reply. Remember, reply is our type that we defined in our protobuf definition. So we're going to go and just start keeping track of the time. We're going to get our range from the request. This is kind of significant. Async code and sync code don't play nice together. Has anybody read the blue functions and red functions paper? Well, you're not going to escape that, not in Rust. I'm currently of the opinion that it just comes with the territory. If you want to finagle in things that are trying to be high performance, that's just something you can't escape, really. I've seen some proposals for making the await implicit and some other things, but I remain unconvinced.
I don't understand what the point of using async code is here.
So the actual point almost doesn't matter here. It matters.
Line blocking and then using threads for all of our calculations.
Yeah. No, essentially, in this particular instance, it's more toy than practical. Just to try to make it practical, I have, remember when we brought in request, I am making a HTTP call out somewhere. And so these two things can be done in parallel asynchronously. So this is, maybe I should have included this code in the slide.
Well, I mean, doesn't spawn blocking itself use a thread?
It does.
So, I mean.
So that it doesn't block
pretty
the
much
synchronous thread.
Threads all the way down, you're just managing the threads with async code.
Yeah, well, so maybe this example would have been better if this wasn't a computationally intensive task to do the Callouts thing. You could imagine, let's say that
Like
I'm
if
calling
that was
this.
calling out to its own back-end service to do the computation, this would
Yeah.
be perfect for async because it'd make that call and keep doing its async stuff.
Yeah, well, this will kind of do that in a way that it will go and put this in whatever threads it's going to do, and then it can do this getCatFact is returning this future, and so it can manage
Is it doing
that.
those two things at the same time?
It is, yeah. Well, and the reason it's doing those at the same time is because of this Tokyo.join. We saw it in the example earlier, but essentially this says, look, both of these, do them concurrently. When they're both done, get me the results. So we get the result of the message. I also decided to include calling the getCatFact one more time with an await, just so we could see that syntax in action. I think that this turns off some people doing the dot await for, instead of like in JavaScript where you have a wait and then the promise that you're trying to await. I've actually found the more I use this, I actually prefer it because it means you can chain futures far better than you can in JavaScript. Then well, I should have broke this into multiple lines, but I didn't. So we formulate our reply, create a response with the reply, and this match statement is becoming what is returned as part of this compute function. And there's actually some more boilerplate that goes into it as well, but it doesn't fit on a slide very well. So we can actually go and look at this as it runs. This isn't fitting on the screen. I hope it maybe over the internet it fits better, but can I? Okay, sweet. Let's try to run our actual code, start up our service. On the left, I've decided to leave up htop so we can see the processors. This doesn't fit very well on a size-constrained screen. But on these right two panes, I have a little gRPC curl program so that I can make calls to our gRPC server. And really simply, I can make a call to the server, see that the CPUs are going crazy, and make some concurrent calls at the same time. We do get how long it took to do the computation, and we get our little cat fact from this random API I found on the internet. So if we go and run these at the same time, they're able to manage our concurrency fantastically. There's a lot that you can do with
cat facts.
yeah. Easiest API I could find to go and slap that together. There's a lot more that you can do with Async Rust. Async Rust, some of the benefits you also get there are easier cancellation of tasks, and there's this whole other world of Async Rust that would maybe be better in a separate talk. But essentially, that's all I have. Thank you for listening.
Good job, Michael.
Thank you.
So, you did a lot of stuff for performance here, and you talk about correctness as well, and I go back to what I was attracted to Rust. It was all about, I needed the performance, and that's why I first thought about using C++. The thing about using that language again, the choice to use Rust as opposed to C++ was all about the fearless concurrency, the memory safety, all about just knowing that even though I have a learning curve learning it, I was not going to spend this infinite amount of time on the back end trying to debug my stuff and worrying about what would happen in production. In my area of work, I'm not doing web programming. I'm putting code in $500,000 devices that I send out to major pharmaceutical companies. If it doesn't work, we've got to send a technician out there or do something. They don't allow network connections inside their company. You know, it's a big deal when something fails. I just don't go in there and shout SHH into it, go fix it. And if you only have 100 customers, unlike JavaScript that has 20 million people pounding against that library or whatever in big side noise, there's just no way we can advantage of that massive number of people just testing your stuff to test it online. You just have to know that if I compile it and I run through some perfunctory tests and I send out, I just know it's going to work. And Rust is the only language that I felt I can do that with comfortably.
Yeah, a sentiment that I have and that I've heard again and again is, yeah, it's a pain to get it to compile, but when it does, I mean, it's working. Yeah, which has been not just a sentiment I've heard, but it's been absolutely true. It's really nice.
But I do know that there's other cases where, like I think data science is a lot like this, where a lot of data science is just one person on a computer doing things themselves, experimenting. And they just want to get something going quickly. So using a language that's dynamic, it's not too thicky like Python, where just for the limited case that you're thinking about in your case, and this thing goes wrong, you can fix it yourself, it is all about the time to development. The real performance constraint then is not how fast the code runs, because even the slowest Python is faster than the fastest human. It's about how much time does it take me to get there. But on the other extreme, I'm looking forward to Rust getting into Linux or getting into other things that are very large. If I have 20 million devices running that system code, and it's just 10% faster, or it's 30% faster like we saw in some of those examples, that adds up quite a bit over that very large scale. But I think what we haven't talked about yet, I think we talked a little bit before, is the memory safety, about how 70% of all the security errors, both Microsoft and Google have come with about the same number, saying 70% of all security breaks are about memory handling errors that Rust would essentially eliminate.
Well, and I think it's safe to assume that those programmers, those C++ programmers, are amongst the best in the world, like best of class when it comes to C++. If you're doing Chromium, if you're working in Windows, you're no novice. And even there, those large code bases, yeah, those memory safety issues crop up a lot.
The strange thing about even really, really smart people often like to build very complex things. And maybe the constraint of what you're trying to do pushes you to the edge of your intelligence to handle that. But we all know code has bugs in it that you don't think of. So by the definition, if you use all your intelligence to build the most complex thing you can, given that there's a defect in there, by definition it's more complex than you can understand.
Yeah.
So it's impossible to debug the thing on your own.
Well, even
Gosh, I want that on a placard.
Probably exists.
yeah.
It was beautiful.
Well, the other thing is, like, we talked about RAII, where like how do you know that things are initialized? How do you know that the expectation has been met when you're using someone else's code, right? If you're getting in this huge code base where you have many other developers, there might be some implicit thing about the environment that you didn't initialize, that you didn't know was expected. And so it's almost nicer to just know that when you're using somebody else's code, oh, I've fulfilled whatever your expectations are when I use your code, I've fulfilled it.
Does anyone here for their production environment use a static code analysis tool like Sonar Cloud or anything like that?
I haven't in the past.
Yeah.
So we do that, it finds stuff.
Every time.
But that's when we're using like Java or C# or things like that. But I think of it, no one supports Rust. Why? Because everything's built into the compiler, and the parts that are Clippy will do for you. That
Yeah.
If you use the compiler, use Clippy, there's no need for a market to produce a tool to, I mean, people may argue they want to use a different formatter or something, but there's nothing about showing that the code is correct.
Yeah, the compiler will get you 90% of the way there, and Rust Clippy will get you the extra 40%.
Good. We've only got a little bit left until we know the program's correct.
I've actually been surprised at how much Clippy could speed up my programs. Just like,
Yeah.
what?
No, the hinting.
I didn't realize I was doing something inefficient. And Clippy's just like, it
Yeah.
could be faster if you tweak it and do this.
I mean,
Who needs GitHub Copilot? We got Clippy.
Well, something else I love about Rust is the constant education. That's what's really cool about Clippy. Is it's not just like, oh, you're wrong, go you find your seg fault.
this is what you should be doing.
Yeah, it's like, and this is why. Go click the article. You go figure out. We'll show you why.
Mm-hmm.
It makes you a better programmer to read and use. It's cool.
I've heard some people say the same thing. They may have to, for their day job, go back, in my case, again, working in the C++, go back to C++. But after having mastered what the borrow checker does, they realize that what they were doing before was working by coincidence.
Yeah, like the Go code. If you
There was a lot of Go code that worked by coincidence up until Go 1.6.
That's true.
I have
When
no
they
contest.
changed the
For,
default for Go Max procs. Yeah.
what is that?
Well, so it used to default to running all your stuff on one thread. So you could use a bunch of Go routines, but they all ran synchronously. Like
Interesting.
they ran in distinct.
So it was
chunks.
concurrent, not parallel by default.
Correct.
Yes.
It's when it moved to parallel.
Yeah, it's when they were like, we'll default to the number of cores you've got. Change things.
So I remember it was probably around 1998, 1990, maybe 2000, but when you first started getting motherboards that had, I mean, you didn't have multi-core chips at that point. You started getting motherboards with two chip sockets. You get two CPUs. And we, for our embedded application for a $200,000 machine, got that. And all sorts of bugs in our C++ code came out because we were always.
So I've got a buddy who says he gave the definition of mixed company being people that you do and don't trust. Because when he was a kid, he didn't understand what it meant, and since then, it's hard for me to not think that that's what it means, because that sounds such a good form of fix. Anyway, so for those of you joining in online, thank you for joining in. I'm going to just, hello. We're going to end the online presentation now, so we can talk work secrets and politics and other terrible things. And so y'all have a good one. If you liked it, give it a like. If you didn't, give it a thumbs down. If you liked it, share with somebody you like. But if you didn't like it, share with someone you don't like. And feel free to subscribe. Adios.